This lesson's about water, and here are your objectives. So we should ask ourselves, when astrobiologists are looking for signs of life on other planets, why is it that they're often looking for signs that there was water there? Here's a molecule of water with an oxygen and two hydrogens. And the first thing that's important to recognize is that these covalent bonds, indicated by the sticks here, are polar covalent bonds. The electrons in that bond are not being shared equally. They're being pulled closer to the oxygen. There are the electrons there being pulled closer to the oxygen. And because there's more electrons over on this end, it gets a partial negative charge. That's how we would write this. And this end gets a partial positive charge. Both of the hydrogens are having electrons stolen away from them a bit. That gives the whole molecule a dipole. So just to back up for a moment, recognize that this bond here is a polar covalent bond. Now, that means that the next molecule of water over, let's say there's another water molecule over there, will orient so that its partially negative oxygen is close to the partially positive hydrogen. And then we get an intermolecular bond, or an intermolecular force shown here, and that bond is called a hydrogen bond. So a hydrogen bond is an intermolecular bond, and it's not actually as strong as the polar covalent bond that's within the molecule, but among intermolecular forces, it's extremely strong. And hydrogen bonds are at the center of what makes water so special. So because water molecules hydrogen bond to each other, they exhibit a property that's called cohesion. You can think of the co in cohesion as cooperating or being together, so that can help you remember that they are bonding to each other. And the cohesion of water leads to important properties like, for example, transpiration pull in the xylem of plants. Now, the way that water moves up in plants, for example, think of a tall tree and water being able to reach the leaves. The way that that happens is that water moves out of the leaves by evaporation, and each water molecule is connected to the water molecule before it in a chain. Think of a conga line by these hydrogen bonds and these, therefore, cohesive forces. And so each water molecule pulls the water molecule behind it up the tree. So that's an example of how cohesion is important in transpiration pull in the xylem, and we'll learn more about this when we get to the plants unit. Also, in that same phenomenon of transpiration pull, the water molecules are attaching to the polar molecules in the cell walls of the xylem, and that's a property known as adhesion. Adhesion is when molecules are attracted or attaching to other kinds of molecules, as opposed to cohesion being the same kind of molecule. And so here, same phenomenon, transpiration pull, the polar water molecules are attaching to the cell walls in the xylem. And just like holding on to the side of a rock climbing wall would help you get up, holding on to the polar cell walls helps the water molecules climb up the tree as well. So hydrogen bonds are important in a number of ways, cohesion and adhesion being the first two. As well, because hydrogen bonding takes place between molecules of water, it takes a lot of energy to get them to jiggle around more, to increase their kinetic energy or their energy of movement. And as a result, they have what's called a high specific heat capacity. That means that it takes a lot of energy to raise their temperature. So it takes a lot of energy to raise the temperature of water. And that's why coastal areas are generally more moderate in their temperatures, because they have water, large bodies of water near them that don't increase and decrease their own temperatures very much, and then that water helps to cool or warm the land. Deserts, in contrast, tend to have very sharp changes in temperature, get very hot and very cold, because there's not a lot of water, demonstrating this high specific heat capacity. You can also think of this as temperature inertia. Inertia is the property that resists changes in motion in physical objects, and here high specific heat capacity acts a bit like that. It resists changes in temperature. And that's because to raise the temperature, you need to increase the kinetic energy, get the molecules to jiggle around more. Also, it's hard to give the water molecules enough energy that they leave the water entirely to become a gas, and that's called having a high latent heat of vaporization. Imagine that to get a water molecule to leave the water phase and go into the gas phase, you need to break it off entirely. You need to give it even more kinetic energy than you did above. So it takes a lot of energy to go from a liquid to a gas. And this property is why we sweat, to cool ourselves. When the sweat evaporates, it actually takes a lot of energy to make that sweat go from liquid to gas phase, and that energy is drawn off from our bodies, and that's why sweating is an effective mechanism of cooling. It's also why on a humid day we feel warmer. So it's not that the temperature is warmer, but we're less able to get rid of energy, heat energy, by evaporating our sweat, because the sweat just doesn't evaporate as well. So that's why we feel warmer. So sweating is an example of making good use of the high latent heat of vaporization of water. Lastly, because water is very polar, it dissolves other polar compounds. You've probably learned in chemistry that like dissolves like. So if you had a, let's say you had a sodium ion here, there's my sodium ion, and it's going to get surrounded by, because it's positive, it's going to be surrounded by the negative parts, the oxygen part of water molecules, and that will solvate it or dissolve it. So polar, or in fact in this case charged molecules, ions or atoms, are very soluble in water. In contrast, something like a hydrocarbon, like this, which is just carbons at the corners and hydrogens everywhere else, is completely nonpolar, and it's not going to dissolve in water very well. So it's because of those properties, all really down to hydrogen bonding, that water is so important for life.